Picture a wooden ship hundreds of miles from shore, surrounded by a blinding storm. Before GPS or reliable maps, navigating the open ocean under heavy clouds often meant guessing your way through the dark, hoping you didn't hit a reef. To survive, some sailors relied on an unusual tool. They would take a piece of a specific dark, jagged rock, tie it to a string, and let it hang freely. After spinning for a few moments, the rock would come to a dead stop, always pointing in the exact same direction. Ancient seafarers across the globe observed similar phenomena. In India, navigators used the Matsya yantra, a small fish-shaped piece of iron that, when floated in a bowl of oil, would reliably rotate to align itself along a north-south axis. The sailors couldn't see what was pulling the rock or the iron fish, but they learned to trust it. They were using early versions of the compass, tapping into an invisible physical force to find their way home. By observing how these specific stones reacted to their environment, early humans took their first steps toward understanding and measuring the unseen rules that govern the physical world. To find the source of that unseen pull, we have to look inland. In the ancient Greek region of Magnesia, shepherds walking through certain fields noticed an unusual problem. The iron nails in their sandals and their iron-tipped walking sticks kept sticking to the ground. The soil in these specific fields was rich with a naturally occurring mineral. We now call this dark, iron oxide-rich rock magnetite. Because sailors eventually used these specific rocks to lead their ships across the ocean, the stones earned the nickname lodestones, which literally translates to leading stones. A magnet is simply any object or material that produces a magnetic field, giving it the ability to pull or push specific materials without physically touching them. The phenomena that startled shepherds in the fields of Magnesia provided the physical evidence needed to study this force. Their region even gave the interaction its permanent scientific name, magnetism. Those jagged pieces of magnetite were natural magnets. Today, we mostly rely on artificial magnets, the sleek manufactured bars and horseshoes you might see in a classroom or holding up notes on a refrigerator. If you hold one of these artificial magnets in your hand, you might wonder how far its power extends. Does it exert a pull on every object around you, or even every piece of metal? It actually ignores the vast majority of materials. Sweep a strong magnet over gold, aluminum, or copper, and nothing happens. But bring it near specific elements like iron, steel, nickel, or cobalt, and they will leap across the gap to stick to its surface. This shows us that magnetism is a highly selective interaction. It operates on strict physical rules, dictating exactly which atomic structures can be manipulated by the force and which are left entirely alone. To understand those rules, we have to look at the structure of the magnet itself. Every magnet, no matter its shape, has two distinct ends where the pulling force is strongest, the North Pole and the South Pole. A magnet's influence projects outward, creating an invisible three-dimensional magnetic field. When opposite poles face each other, their fields connect and pull together. But if like poles face each other, the fields clash and push apart. This repulsion is the definitive test of magnetism. This invisible architecture of poles and fields creates a predictable set of physical laws. Whether you are holding two tiny paper clips or operating heavy machinery, magnets will always obey these exact rules of attraction and repulsion. Knowing these rules helps explain the mystery of those ancient sailors. If a suspended rock always points in one specific direction, it means its magnetic field must be interacting with another, much larger magnetic field. The Earth itself is a giant magnet. Molten iron churning deep inside its core generates a massive magnetic field extending far into space. The sailors' compasses were simply aligning their tiny poles with the Earth's massive magnetic poles. Modern industry scales this force using electricity. By running an electric current through a wire coil, we create electromagnets powerful enough to grip and lift tons of scrap metal at once. We apply this exact same principle across high-tech infrastructure. It drives MRI machines using strong magnetic fields to map the inside of the human body, and maglev trains, which use magnetic repulsion to float friction-free above their tracks. From the compasses of ancient explorers to the diagnostic tools in our hospitals, magnetism provides the invisible framework for much of our technology. Understanding the simple push and pull of a lodestone allowed us to harness a force that spans the entire planet.